Okay, good morning. Let's get started. So today we're going to discuss about the gradient calculation, right? Because in the last lectures we saw that calculation of secondary gradient would actually mean that calculation of a phase gradient, right? That's what we kind of reduced in the last class. So calculation of secondary gradient on the phases was reduced to the calculation of gradient of the scalar on the phase, right, in the xi direction, right. So this is a gradient on the phase in the phase normal direction, that is what we wanted to calculate. If we can calculate this, then the secondary gradient can be evaluated accordingly, right. So today we are going to look at gradient calculation. So one of the reasons to calculate gradients is of course its requirement in the calculation of secondary gradient. Okay, so secondary gradient calculation requires the gradients of the dependent variable on the phases, right. There are several other instances where the gradients of the dependent variable are required, and those are, for example, let's say if you are solving for complete Navier-Stokes equations, right, then we need to calculate what is the pressure gradient, right. So in the calculation of Navier-Stokes equations, we have the pressure gradient term which needs to be calculated. Okay. Now we also note that it is not just the gradient in the direction of the phase that is required, but rather the gradient in all the directions, right. All the components of the gradient are required here. Okay. All the I, J, K components are required, not just in the direction of the phase as is required by the secondary gradient. Okay. Further, let us say if you have a non-Newtonian model for your viscosity. So if you have a non-Newtonian model, for your viscosity, then we again would need gradients of velocities, right, because your gradients of velocities are required in the non-Newtonian coefficients that have to be calculated. So as a result, we need to calculate what are the gradients of the velocity, right. Here u would be your phi, right, is required. Similarly, if you have, let us say if you are solving for turbulent flows, let us say if you have a statistical model, so let us say something like a Reynolds Navier-Stokes model, something like a K epsilon model or something like that, then the production terms in these turbulence models would also require the calculation of the gradients. Okay. So the gradient of the velocity vectors are required in evaluating the production terms of the RANS models. And further, let us say if you have a large eddy simulation model, something like a Smagoronsky model or so, then the subgrid scale stresses that we get, that is the tau ij, the subgrid scale tau ij superscript SGS, would also require the filtered velocity gradients. Okay. So which are basically the dependent variables that we are solving for. Okay. So we would need gradients in any one of these instances or in all of these instances. Okay. So as a result, we need to kind of seek a particular way or a method of calculating the gradients for the dependent variable. Okay. So that is the motivation to kind of come up with a method that can calculate the gradients of the dependent variables. Okay. So there are several methods of course to calculate the gradients, but we will only look at a couple of standard methods, and this is an ongoing area of research. So you will see research articles coming in with new methods to calculate the gradients which are more accurate and so on. Okay. So we will only look at two standard ways of calculating the gradient. The first one is the gradient theorem approach. This is also known as the Green-Gauss method. and the other one we will look at is known as the least squares method or the least squares approach. Okay. These are two standard gradient calculation methods that are also available if you use any simulation software as well. Okay. Fine, let us look at the gradient theorem approach or the Green-Gauss method. Okay. So, in this we kind of invoke the gradient theorem to calculate the gradient of the dependent variable phi. Okay. So, we have already seen the Gauss divergence theorem, right, in which we converted a volume integral into a surface integral for if you have a volume integral in the form of a divergence of a vector, right, then you could convert it into a surface integral, right. But gradient theorem is something different, right. Gradient theorem is for gradient of a scalar integrated on a closed volume, right. Let us say, so we are considering a closed volume, right, that is enclosed by surfaces. Okay. These surfaces that enclose it completely close the volume, right? There are no openings. So, we consider a cell of to be of the same to have the same property. Okay. Then if we have a closed volume delta V naught, what would the gradient theorem say or the Green-Gauss theorem say? So, we have a delta V naught volume, right. In this volume we want to calculate gradient of a scalar, phi is my scalar and dV would be the differential volume, right. What would gradient theorem relate this gradient of the scalar to the surface integral as? So, up till now we saw what is del dot phi, right. If we had del dot phi, we wrote it as phi dot dA bar, right, or del dot phi bar, right, some kind of vector, right, in the Gauss divergence theorem. But now we are talking about gradient theorem, right, where phi is a scalar and the gradient of the scalar is what we are calculating in the volume of the cell, right, that is delta V naught. What would this be related to? This would be, can be converted also into a surface integral, right, integration on the area, integral over the control surface. What would be the quantity here? Phi dA bar. Is that correct? Is it correct dimensionally? What is on the left hand side? You get a vector, right, gradient of a scalar. What is on the right hand side? Right, it is also a vector. You are adding the phi on essentially on the all the areas, right. Okay, you are summing it up. All right. Now, if I assume that the gradient of the dependent variable phi is a constant in the entire cell, right, I am essentially making a mean value approximation. So, essentially this is the gradient theorem, which relates gradient of a scalar integrated over the entire volume to be equal to sum of the scalar multiplied by all the vector differential areas on the entire surface, right. That is what the theorem says. Now, if I use a mean value approximation and say that the grad phi at the cell centroid is a representative of the entire cell, right, and grad phi remains a constant inside the particular cell that we are talking about. Okay. Then I can, can I rewrite this integral into something else? Can I evaluate this integral? Grad phi is constant wherever you go in the cell, then what would be this integral? Grad phi times delta V naught, right. So, this would be grad phi times delta V naught, and this is grad phi 0, right, essentially that is for the cell, equals, again if I use a mean value approximation, right, for the phi on the faces, right. Let us say my control surface is made up of several areas, several faces, and all these faces are planar faces, and the value of the face of the phi on the face is basically taken as the face centroid value, right. If I do that, can I replace this integral into a summation, right. Okay, this will be a summation sigma f, right, and what would be this? This would be phi times a f bar, right. This is phi a f bar summation f, right. Here actually this control surface integration has two components. One is integration over the little area, other is sum of all these areas, right, for the phi times a bar, a f bar. Okay. So, this is the discrete form of the gradient theorem. Now, do you see why it is useful to calculate, why is this a method to calculate the gradients? You will see it right away, because what are the inputs for this? Phi is the input, right, which we already know from the previous iteration value or the current iterated value. Do we know a f bar? We know areas. What about the cell volumes? We know. And what do we need to calculate? Grad phi, right. We just need to calculate this grad phi of 0, right, at the cell center. Okay. That is as simple as that. Of course, we do not know phi exactly on the faces, right. That is one thing we do not know, because phi is only stored at where? At the cell centroid. So, we need to kind of devise a way of calculating phi, interpolating it to the faces from the cell values, that we need to do. Okay. But if I rearrange this equation, we can say grad phi for any cell can be calculated as 1 by delta V naught summation f phi f a f bar. Okay. Of course, we need to come up with an interpolation scheme to evaluate phi f from the phi 0 and phi 1 values. Okay. So, let me begin with a crude approximation. Okay. Let me assume that I would calculate my phi f as an arithmetic average of the phi 0 and phi 1 values. Okay. Now, this is not correct, right. This is only correct if you have uniform cells. If you do not have uniform cells, this has to be replaced with a linear interpolation, right. Need not be harmonic mean. It can be, it is not arithmetic mean, it will be a linear interpolation. You need to get a factor f, right, which is basically the distance between the face and the cell centroid p and 1 minus f and so on, right. So, as of now I am assuming that it is just an arithmetic mean of the cell values. Okay. We know that this is not correct if you have non-uniform meshes. Okay. But what we will do is we will try to improve this phi f little later, okay, in a different way. Okay. So, this is, so I assume phi f to be the cell centroid values average, and now can I use this phi f values in the equation above and calculate the gradients? Of course, I can calculate, right. If I do that, then I am going to get grad phi at every cell that I have, right. So, if I have a cell bounded by 5 faces, this will be summation of the phi of a f bar on all the 5 faces, right, divided by the volume, that will give me gradient and so on, right. Then this way I can calculate what is the gradient of the dependent variable phi. Of course, we know that this is not quite correct, right. So, what we do is we try to improve this by saying that if you look at the cells, let me draw typical cell here. So, this is the face centroid, let us say, this is the face centroid, okay, this is the cell centroid. So, we are talking about C 0 and this is the face f, this is our A f bar and this is my C 1, right, that is what I have, and this is the face centroid. Okay. So, and these distances are not the same. Okay. So, then what I would do is I would say I would draw a line connecting the cell centroid C 0 to the face centroid. I would call it as delta R 0 bar, okay, and I would connect the cell centroid to the face centroid. I would call it as delta R 1 bar. Okay. These are two vectors that connect the cell centroids to the face centroids, which can be done. Okay. Now, can I use Taylor series expansion, not in just 1D, but a general Taylor series, and relate what is the value of phi f from phi 0, right. If it were a 1D, we know that how to do it, right. Essentially phi little e was written as how much, phi p or something, right, plus we wrote we wrote it as partial phi partial p partial phi partial x at P, right, times delta x, right, and so on, right. We could do it in a 1D expression, or we had used x minus xp, right, if it were not the east face. Okay. Similarly, can I use now? I cannot use 1D because this is connecting delta r0 bar, right, which is a particular vector. So, can we use a general Taylor series and relate what is phi f or evaluate what is phi f purely from phi 0 values. So, I want to reconstruct phi on the faces from phi 0. Can I do that? Of course, we can do it, right. So, we just expand this thing. So, this will be in a similar sense phi 0 plus what would this be? This would be grad phi 0 dotted with delta r0 bar. Is that correct? Essentially, we get terms like partial phi partial x times delta x plus partial phi partial y times delta y plus partial phi partial z times delta z if it were 3D. Right. Essentially, that will be the dot product of the delta r bar with the 3-dimensional gradient. Okay. Of course, if you want to do it higher order terms, you would have del square phi 0 and so on, right, which we are not writing here. Fine. Okay, then can we do the same thing? Can we reconstruct the phi f from phi 1? Yes, we can do that. Okay, so what will that be? That would be phi f equals phi 1 plus grad phi 1 dotted with delta r1 bar plus higher order terms. Is that correct? Okay, I have chosen delta r0, delta r1 bars to always point to the face centroid from the cell centroids. Okay. So, we do not have any confusion. Now, can I now I have just computed what is grad phi at each and every cell, right, that is grad phi 0 is calculated, grad phi 1 is calculated, these are known, right, and these vectors are also known from the mesh that we have created. Do we know the guess values for phi 0, phi 1? We know these things, right. So, now can I calculate what is my improved value on the face as an average of these two? Right. Okay. So, that means I can calculate my improved phi f as phi 0 plus grad phi 0 dotted with delta r 0 plus phi 1 plus grad phi 1 dotted with delta r 1 bar, right, divided by 2. Okay. Now, this is not as crude as we had started off with, right. We started off with only the first terms in here, right, only we said phi f equals phi 0 plus phi 1 by 2, but now we have an extra term here, which is the second term in the Taylor series expansion. So, we have a little bit improvement compared to what we had started off with, right. Okay. So, now the general algorithm is use this phi f back in the equation, okay, back into this equation and calculate what is the improved cell centroid values. Okay. So, in the process we have set up an iterative scheme where we start off with a crude approximation for phi f, right, use that, calculate the gradients, use the gradients again to improve phi f and then update the gradients, right. Now, this can go on for few iterations until we reach a converged gradient values, okay. But generally you do not do more than couple of iterations, 2 to 3 iterations is sufficient. Why are we iterating here actually? What is the need for iterations here? Which term is actually making us to do this iteration? Essentially the approximation for phi f, that is the truncating the terms in the Taylor series, that is what is making it. Okay. So, essentially couple of iterations is enough. So, 2 to 3 iterations are sufficient. That is what is done in the actual solvers if you look at. So, if I were to write a general algorithm for this, what would that be? That would be, so this is gradient theorem approach. What do we do? What is the first step in the algorithm? You calculate, you guess what is, you evaluate what is phi f from the existing phi 0, phi 1 using arithmetic average, right. What is the next step? Calculate what is gradients of phi, this is gradient of phi at the cell centroids using the delta v 0 sigma f phi f a f bar, right. Then once you have calculated gradients for all the cells, improve phi f using what? Using phi f equals phi 0 plus grad phi 0 dotted with delta r 1. Did we use delta r 1 or r 0? R 0, okay, plus phi 1 plus grad phi 1 dot delta r 1 bar divided by 2. Now, use updated phi f and calculate, essentially go back to step 2, right. That is basically go back to step 2. Go to step 2 and repeat. Okay. Usually, couple of iterations are sufficient to get a converged grad phi. Fine. Questions on this? Is it clear? Okay. So, if I give you some mesh with these area vectors that you can calculate and some phi values, you can calculate what are the gradients using this approach, right. You can also code it up, fine. All right. So, this method is very generic method, kind of works. It is a generic method and works on unstructured meshes. Okay. So, we do not need any special features here, okay. It kind of works on general unstructured meshes. All right. Okay, let us move on to the next method, that is the least squares method. Any questions till now? No? Easy? Okay. Let us look at the second method, that is the least squares method. Now, the idea in the least squares method is to reconstruct the neighboring value of phi. Okay. So, essentially reconstruct neighboring cell value from the present cell value. Okay. Now, how do you reconstruct this accurately? Gives you the value of the gradient. Okay. So, we want to calculate what is phi at 1 cell 1 from phi 0 using certain gradient grad phi 0. Okay. Now, we want to calculate this, evaluate this phi 1 as accurately as possible, then what would be my grad phi 0? That is the idea. Okay. So, essentially evaluate or obtain grad phi 0 such that you reconstruct neighboring cell value from present cell value accurately. Okay. Okay. Then let us have a look at a particular mesh configuration. Let me draw a mesh here. Okay. I would use some mesh we have not seen till now, something like this. Okay. So, we have a mesh here that need not necessarily have the same number of edges. Okay. Okay, I created some mesh here. Fine. So, let us call this as C0. The value here would be phi 0. Okay. And let us call this as C1, C2, C3, C4, C5, C6 and so on, right. This can be very different. Now, I also want to draw some lines here, that is basically we want to calculate what is phi 1 from phi 0 using the gradient at phi 0, right. That is what we want to do. So, let me connect C0 and C1 using one vector. This is basically delta R0 or R1 bar. Okay, let me call it delta R1 bar. Okay. Can we obtain delta R1 bar? We can, right? We know the cell centered values. So, if I were to calculate what is phi at 1 from phi at 0, how do I obtain this? Using general Taylor series. Phi 1 equals phi 0 plus what do I need to know? Gradient at phi at cell centroid. This would be plus grad phi 0 dotted with delta R1 bar, right? That is correct. Okay, that means now delta R1 bar definition is different from what we had before, right? Earlier delta R1 bar was connecting the cell centroid C1 to the phase centroid. Here it is the distance or the vector connecting C0 to C1, right? The cell centroid vector. Okay. What about phi at 2? Can I obtain phi at 2 from phi 0 and the gradients? I can, right? Phi at 2 would be phi 0 plus grad phi 0 bar dot delta R2 bar, in which case I have to define what is delta R2 bar as line connecting C0 and C2, right, and so on. And I would have delta R3 bar, delta R4 bar, delta R5 bar and delta R6 bar and so on as many number of neighbors I have. Let us say if I have m neighbors, I would have to have m of these equations, but there is a problem that you can see right away, right. There is a problem in this approach. Okay, we will come to that problem. So, essentially the idea is now how do I obtain this value? This is the unknown, the grad phi 0, such that I can accurately calculate not only phi 1, but also phi 2 and also phi 3, right, and so on, because all of these would use the same gradient at the cell center C0, right. So, I need to calculate grad phi 0 as accurately as possible, such that this gradient value at the cell centroid will give me or will help me reconstruct the neighboring cell values correctly in some sense, right. Okay, that means if I have let us say a j neighbor, phi j would be what? Phi 0 plus grad phi 0 dot delta R j bar, right. And similarly, if I have m neighbors, this would be the mth equation, right. This would be the mth equation if I have m cell neighbors, right, that share a phase. Okay, that means how many equations do I have? How many equations do I have? M equations, okay. I have m equations, all right. Now, what would be, let us say I consider a 2-dimensional situation, we are talking about a calculate the gradients in 2 dimensions, okay. Then what is my grad phi 0? What is the definition for grad phi 0? I hat partial phi partial x at 0 plus j hat partial phi partial y at 0, right. This remains the same. What about delta R 0 bar? If you were to write it as a vector, this would be I hat delta x naught, right, plus j hat delta y naught. What is delta x naught? Oh, sorry, we do not have delta R 0, right, we have delta R 1. So, all these should be sub 1s, right. So, this is delta R 1 bar, delta x 1, delta y 1, right. What is delta x 1? X 1 minus x 0, right, the x component distance between cell 1 and cell 0, okay. Fine. So, we have this. So, what is this product delta phi bar dot delta R 1 bar that we have in each of these terms, right. We have this product here, right. What would this be? This would be basically delta x 1 sorry, delta x 1 partial phi partial x 0 plus delta y 1 partial phi partial y 0, right. That is what we have. That means, I can rewrite this equation. If I send this phi 1 to the right hand side or phi 0 to the left hand side, I can rewrite this equation, this particular equation as what? As delta x1 partial phi partial x0 plus delta y1 partial phi partial y0 equals how much? Phi 1 minus phi 0, right. Similarly, I can write an equation for the second cell value that we reconstruct as delta x2 partial phi partial x times 0 plus delta y2 partial phi partial y0 equals phi 2 minus phi 0, right, and so on. Delta xm partial phi partial x0 plus delta ym partial phi partial y0 equals phi m minus phi 0 if we have m cells, right, or this would be j for a particular jth cell. Okay, now we have as many equations as we have number of neighbors, number of phase neighbors, but what is the unknown in this? Phi, is phi the unknown? Gradient of phi is the unknown, right, partial phi partial x and partial phi partial y at cell 0, right, this is the unknown. Phi 1 phi 0 are known from the current iteration values and deltas are known as the from the mesh, okay. So, these are all known. So, that means if I were to write this in a matrix form, can I write it in a matrix form? Okay. How many equations I have? M equations. So, how many rows should my matrix have? M rows, and what are the coefficients? Delta x1, delta y1, delta x2, delta y2 and so on, delta xm, delta ym. This is my matrix times what would be the other vector that I have? Partial phi partial x0, this should be a column vector or a row vector? Column vector, partial phi partial y0 equals what would be on the right hand side? Phi 1 minus phi 0, phi 2 minus phi 0 and so on, phi m minus phi 0, right. This is what I have, right. I have a matrix equation which has m rows and how many columns? 2 columns. This is an m by 2 matrix, and I have an unknown vector here which is 2 columns, 2 rows and 1 column, and then here I have m rows and 1 column. Okay. So, we have a m by 2, 2 by 1 and m by 1 vectors and matrices here. In general, what is the in a 2 dimensions, what is the minimum cell neighbors I would have? What is the cell, the smallest cell that you can take with minimum number of faces? 3, right, it is a triangle, right. So, in general m is the number of rows would be greater than 2, right, this is always greater than 2, right, because you have at least 3 faces for a triangle. Okay. How many unknowns I have here? 2 unknowns. How many equations I have? M equations. I have m equations and 2 unknowns. Can I solve for this system uniquely? Can I solve this? This you cannot solve, right, because if you use 2 equations you get a solution, you get 2 other equations you get another solution. You cannot satisfy all these equations at once, right. That means this is a what type of a system? Over specified system, right. So, this is basically over determined or over constrained system, okay, for which we cannot you do not have unique solution, right, because if you take 2 sets of equations you would get 1 solution which will satisfy only those 2 equations and not the other ones, right. So, this is nothing new to you because you have already come across such systems many a times, right. When you do an experiment you end up having let us say if you are doing an experiment you get some values here for the let us say phi and some x values, you got some values here, right, and you have to fit a essentially you have to find one equation, one straight line that passes through all of these things, right, but you cannot find one equation that passes through all of these things because you have too much data, right. What do you do in that case? You would find you would kind of minimize the error, the square of the error in an absolute sense, square of the error, minimize it and draw a line, right. Now, that line would it pass through any solution? It will not satisfy any of the points, right, but it will be in in a sense it will have the least error possible, right. So, essentially you would say, okay, I have calculated the equation, this is my equation, right. So, this is my what do you call least square fit, right. This is the least square fit line which will not satisfy any of them, but it will have the least error if you consider one by one, right. In fact, that is what we have in the present situation, right. You have too much data and you have to calculate what is two components of the gradients, right, for the dependent variable. You just have to calculate partial phi partial x, partial phi partial y from these m equations. So, what we set out to do is we try to minimize this error and calculate what would be these gradients, which will be in a least square sense reconstruct the neighboring values accurately. Okay. Is the method clear what it is trying to do? We will do the remaining part of it, the minimization of the error and so on, right. Okay. Questions on this part till now? So, essentially we are trying to minimize the error, error meaning from the line that we intend to fit between the data, right. Okay, minimize the error. Okay. Questions? Okay, I want you to say something about this matrix. So, essentially this matrix as it is cannot be solved, right. Can you invert it and calculate? No, essentially you have to use any two equations and solve it, right. That is understood. Let us give some names for this matrix. Let us call let's call this matrix as A, okay, and the gradient matrix as some G, and this we would like to call it as this is from some delta of phi, right. So, let us call it as some D, okay, A, G, D. A is the coefficient matrix, G is the gradients, D is the delta of the phi, okay. That is what we have, fine. All right, let us then move on to what do we do in this context. So, we have to reduce the error or minimize the error, and the equation we are working with is basically delta x j partial phi partial x 0 plus delta y j partial phi partial y 0 equals phi j minus phi 0, right. That is the equation we are working with. Let us call this as, let us say, equation 1. Okay. I can rewrite this equation as to calculate the residual, okay, or the error. So, what I mean is now if you know what is partial phi partial x and partial phi partial y at 0 correctly, you will this equation will be balanced, right, and if it is not the correct value, then it will not be balanced, there will be some error, right. Phi j minus phi 0 would be different from what you get on the left hand side, right, depending on how well you calculate these guys, right. Okay. So, what I do is I will define an error or a residual, okay. In the context of computational methods, you would call a residual as whatever is the difference between left and right hand sides in an equation, okay. So, or an error saying that the difference between the left side and the right side is my error at that cell or at that face, okay. So, I would like to call it as some residual R j. R j is basically I bring the right hand side to left hand side. So, this will be delta x j partial phi partial x 0 plus delta y j partial phi partial y 0 minus phi j minus phi 0 is my residual, right. So, if I use two equations and calculate these gradients, this residual would be 0 for those two cells, right, but that is not what we are trying to do. We are trying to calculate the gradients such that this R j is minimized in a least square sense, okay. Fine. That means, of course, this is just one equation, we have m phase neighbors. So, what would be the total residual R or the square of the residual R? I would like to call it as R j square summed for all the j goes from 1 to m, right. So, sigma R j square would be my square of the error, right. Yes. Okay. So, this is how much? This would be sigma j goes from 1 to m. Let me also write partial phi partial x 0 as some variable a, partial phi partial y 0 as another variable b. Okay. A and b are the unknowns that we intend to get out of this problem. Okay. So, this is delta x j a times delta x j plus b times delta y j minus phi j minus phi 0 whole square is what we have to minimize, right, for this least square error, right. This error is now squared. We have to find the least value for that, right. How do you do least squares when you have two parameters? Differentiate the error with respect to the unknowns that you want, right, unknowns that you want to calculate. So, that means we need to calculate what is partial r partial a and set it to 0, right, and then partial r partial b and set it to 0. Okay. That is what we do. So, we already have the square of the error. We would calculate the least value by differentiating it, minimum value. Okay. So, what would be these equations? Partial r partial a equals 0, what would this be? This would be summation would stay as it is, right. You have a summation. This would be 2 times a delta x j plus b delta y j minus phi j minus phi 0 times what? Times delta x j equals 0. What is the other equation? Sigma j equals 1 to m 2 times a delta x j plus b delta y j minus phi j minus phi 0 times delta y j equals 0. Okay. So, we have 2 multiplying in every term. So, 2 can be thrown out, right. So, this can be taken away because it is there in every term in the summation. Okay, now we got couple of equations. So, how many equations we have? 2 equations, because we have a summation for each equation. Okay. Okay, we have only 2 equations, and how many unknowns we have? Only 2 unknowns. Okay. So, we have now reduced the problem, you see, right. Okay. This is basically sigma j equals 1 to m. How much would this be? This would be a times delta x j square plus b times delta x j delta y j minus phi j minus phi 0 times delta x j, right, equals 0. What is the other equation? Other equation is sigma j equals 1 to m a times delta x j delta y j plus b times delta y j square minus phi j minus phi 0 times delta y j equals 0, right. That is what we have. Okay. We have 2 equations and 2 unknowns. Now, can I try to write this in a matrix form? I can. Okay. So, that would be we have these terms, right. So, the kind of terms we have are basically, if you look at the first equation, how does these terms look like? These will look like delta x 1 square, right, plus delta x 1 delta y 1 plus delta for the first equation it will be delta x 1 square, delta x 1 delta y 1, and then delta x 2 square, delta x 2 delta y 2, and so on, right. That is what we would get. For the second equation you would get delta x 1 delta y 1 plus delta y 2 delta y 1 square, right. This is what you would get, right, plus delta x 2 delta y 2 plus delta y 2 square. Okay. Of course, I have not written a and b here. Okay. I just wrote the coefficients for a and b. Okay. And these are again multiplying with a and b. Can I get this from the matrix we have? So, we have a matrix. What is the matrix A that we have? A is delta x 1 delta y 1 delta x 2 delta y 2 and so on, delta x m delta y m, right. This is an m by 2 matrix, right. What would be, if I were to write A transpose as delta x 1 delta y 1 delta x2, delta y2, and so on, delta xm, delta ym. This would be a 2 times m matrix, right, 2 by m matrix. What would be A transpose times A? Would that give you these equations? Right? So, that means if I write this as A transpose A would be what? Essentially multiply this guy with this guy, right, plus the second one plus the first one with the second column, right. That is your first row, right. A transpose A would be what? Do you see that? You would get delta x1 square plus delta x2 square and so on, delta xm square, plus the first row again multiplying the second column would give you delta x1, delta y1, delta x2, delta y2, and so on, delta xm, delta ym. Do you see that? Do we get that? Yes or no? Yes, okay. What about the second row? Second row would be this one multiplying the first column, right, that would be the mixed values delta x1, delta y1, and the plus the second row multiplying the second column, that would give you the delta y squares. Okay. So, I can write this. Of course, I have the A and B which are nothing but just 2 values, right, which are the same for every term. So, I can put them as a column vector similar to what we had before. I can rewrite these equations that we have, okay, essentially these 2 equations that we have as what? I can rewrite this as A transpose A times the gradient, right, that is basically gives you what will be the size of the matrix A transpose A? 2 by 2, because we have 2 by m by 2, this will be 2 by 2. So, this will be a 2 by 2 matrix, and what is G? Partial phi partial x 0 and partial phi partial y 0, this is 2 cross 1 equals, what is on the right hand side? This is phi j minus phi 0 times delta x j, right. So, you are multiplying delta phi with delta x, and this in the second equation you are multiplying delta phi with delta y and you are summing it, right. So, what would that be? A transpose times. So, if I were to write partial phi, just the phi, this is basically phi, what values go here? Phi j minus phi 0, right, is what goes in here. So, this is basically phi 1 minus phi 0, phi 2 minus phi 0 and so on, phi j minus phi 0, right. Each of them multiplying with 2 rows will give you the 2 equations. This is okay. So, this is nothing but our D or A transpose times D, right, that is your delta phi. This is your delta phi 1, delta phi 2 and so on, delta phi m, which is basically phi 1 minus phi 0, phi 2 minus phi 0 and so on. Now, what is the size of this equations here, this matrix here? 2 by 2 matrix, 2 by 1, and then we have 2 by 1, right. So, this is basically a 2 by 2 matrix, that is all, right. So, and what do we need to do? We need to have, we will have such a system, only one system for the entire mesh, or will it be different for different cells? It will be different for different cells, right. So, essentially you will have one 2 by 2 such system for every cell in the mesh, right. You would calculate that, and then let us say if you have a fixed mesh, the mesh is not changing, what will be the matrix A? Will that remain the same always? The mesh is not changing, A only depends on delta x and delta y, right. So, can you pre-calculate A transpose A and store it? Yes, you can. So, you do not have to do this all the time. So, this can be pre-calculated, right. Right hand side needs to be updated as your phi changes, right, and you need to calculate what is gradient. Okay. So, in fact, you can even pre-calculate what is A transpose A's inverse as well, right, because it is just a 2 by 2 system, right. does not matter how many phases you have, it is always a 2 by 2 system. So, you can calculate this and calculate its inverse and calculate what is the gradient values, right. That means, for every cell you just go and solve this system once and get the gradient values, fine. And the G thus obtained would satisfy none of these equations, it will satisfy only these equations in a least square sense. Okay. So, that is the essence of the least squares method. Okay. Questions? Now, what would happen, will this actually work for a let us say a structured rectangular mesh, would it actually work? Would this method work for, let us say, a Cartesian mesh that is also uniform? Will it actually work for Cartesian structured, or it will only work for unstructured? It should work for Cartesian structured, that is not a surprise. But then what will happen if you have a Cartesian structured mesh which is also uniform? What will happen to this matrix A? What about delta x1, delta x2, all are the same, then what will happen to the matrix A? Then what will happen to A transpose A? Would it become singular? Then you said it will work for Cartesian structure, right? Now we just saying that it will become singular. There is a catch here. What is the catch? They are not the same, because no, the way we have drawn the vectors are all different. What will be delta x? What will be delta x1 and delta x2? They would point in the opposite direction. So, delta x2 would be minus of delta x1 if you have, let us say, a Cartesian mesh, right. In which case the rows are not the same, right. You would have, let us say, delta x1 is 2, you would have 2 and delta y1 is 0, let us say the cells are in the along the x axis, you would have 2 0 and the other one would be minus 2 0, right, and so on. As a result, when you take A transpose A, you would end up with a identity matrix, right. You have 1 0 minus 1 0 and so on, you would end up with an identity matrix with a uniform cell size that is delta x, right, and that is why it would work, right. So, do not get confused, this delta x is not just is not always, it is basically defined in a way that it connects the current cell centroid to the neighboring cell centroids. Okay. Do not use your own definition of delta x here, fine. So, that is important here, fine. If that is the case, it will work for anything. Yes. Only the phase neighbors, yes. Yeah, I think I have not drawn it nicely. Actually, this cell is a little complicated. This is not there. Okay. But the thing is, yeah, I mean, this cell is not there. We are only considering the phase neighbors. Yeah, the figure is drawn a little complicated, but in this context, you may have to use the vertex neighbor also, because this is, yeah, it's okay, because we are not using a linear interpolation between the phases as such. So, you can still consider this thing, right, it can still be left out there. It is just that the other cells are not drawn in a similar way, right. Other questions? So, it will work for regular, structured, Cartesian, uniform, non-uniform, everything, unstructured and so on. Okay, fine. All right, okay, I am going to stop here. See you guys in the next lecture. Thank you.